Hello everyone, and my name is Marcos, and we'll learn some trigonometry. I wanted to make this serious because I think there's not a lot of help for high school students who are struggling with trigonometry, college algebra, even algebra 2, and early level calculus. And it's an important subject, and it's a lot of fun, and it's really interesting. So let's hope that I can help you out. My name is Marcos, like I said, Juan Marcos Savina. I went to, I got my bachelor's in mathematical physics, and that's as far as I've gone. I haven't gone any farther than a bachelor's. So if you guys want any help with quaternions or anything high level, I may not be your guy. But I feel pretty good about this early level math stuff. So let's get to it. Now this is going to be the section on trigonometry, and to start that, let's talk about some things that we need to understand and know before we even get to the trigonometry parts. So mostly just a quick recap of some basic geometry that'll come into play. Um, so what do we need to know? Here I have a tablet I'm going to draw on. We need to know our angles, what degrees are degrees, and our special triangles. Let's start with that. Let's keep it simple. So an angle, to summarize or to remember from our geometry education, is just the measurement that we assign when we have anything like this. Is going to show up. There it is. It shows up. When we have an angle, the angle is the numerical measurement that we have for this figure, right? So what makes this figure? Let's erase this little angle thing so it doesn't get confusing. We have this figure, we'll call it figure A, and then we'll have this figure, we'll call it figure B. What makes them different? They're obviously very different, and you can see that they're different just by looking at them. But how do we formalize their difference? A way that we could do that would be by describing how they look. One of them looks like it's caving in, the other one looks like it's expanding out. And so we could describe them that way. And let's make up words for what these descriptors could be. We could call this acute, and we could call B obtuse. But that's not the best way to describe these, because if you think of, let's look at another angle. Let's look at angle C here. And angle C is kind of like angle A, but it's a little bit smaller. And angle C and angle A are both acute. So if you see angle C and angle A out in the wild, how do you distinguish the both of those? Well, you could say one of them looks like it's closer to closing up, and the other one's not so close. But in this case, we want to numerically describe these angles, and so we're going to assign a number to them. It stands to reason that the smaller the number, the closer it is to closing, the smaller the number it should have. So this should be a very small number. Whereas the bigger the angle is, the bigger the number should be, right? There should be a big angle, a big number. And that just makes intuitive sense, and that's why we've gone this direction. So we have to figure out a way to describe these angles numerically in a way that is specific to any possible angle that could be thrown at you. So what numbers do we assign to these? And this is where it gets a little arbitrary. So the way that we've decided to number these angles is, here, let me see if I can open up a new page. Okay. The way that we've decided to number these angles is based on, let's start with an angle that's here, right? And let's imagine this angle gets bigger and bigger. So it's going to eventually get over here. And then if we keep getting bigger, it's going to get over here. And if we keep getting bigger, it's going to be right here. And then right here. And then finally, it's going to be over here. Right very close to where it started, and eventually it's going to reach back where it started. So eventually it's going to come back here. And if that makes you think of something, it should be a circle. The way that an angle can grow is very circular. It's going to get bigger and bigger and bigger and farther away from where it started and farther away from where it started until all of a sudden it starts to get closer and closer, and then it gets back to where it started. So let's use a circle to describe these angles. So let's draw a very bad circle and then a starting point. So this is where we're going to start. So this is angle 0, or we'll call it 0 degrees. What we've decided, a little bit of, not abstractly, but don't worry too much about why these numbers are the way they are. It would make some sense. You might think to have the whole thing be 100, and then they would all be different percentages of 100, but that's not what we did. When you go to the top here, we call this 90 degrees. When we get to the other side, we call this 180 degrees, and so on and so on. So I think this is 270 if I'm not mistaken, and my math is correct. But you know what? It's always good to check your math, so let's check our math. So this is 180, and we're going to add 90 degrees to it. So 0, 8 plus 9 is 17, and then 270. Yeah. So that is 270 degrees. So what happens here is that at each 90 degree interval, it's a right angle. And that's how we define a right angle. A right angle is defined by 90 degrees. So going back to our previous picture here, let's do that real quick. Now we can describe these more accurately. If we were to get a protractor and measure this angle A, we would see that it would be somewhere around 45 degrees-ish. Angle B would be somewhere around, I don't know, what does that look like? Not good. There's 130 degrees. And then angle C would be something very close to 0 because it's on the other side here. This would be closer to 5 degrees, we'll say. Now, none of these numbers are exact. I'm just guesstimating based on the pictures because I haven't drawn any exact pictures here. So that's just basically how we describe angles. There's nothing to it. If you really want to know like why we're describing angles this way, then you're thinking too much about the angles. There are things that we will have to justify very thoroughly later on. But at this stage, let's just accept there's 360 degrees. Oh yeah, I didn't write that down. There's 360 degrees in the whole circle. So we go 90 degrees over here, and then we go 90 degrees more to 180, 90 degrees more to 270, and 270 plus 90 is 360. So where you start the circle and where you end the circle, that's just depending on your frame of reference. It could be 360 or 0. But anyway, so that's how angles work. The other thing we have to keep in mind, let's take a look at a just random angle. I'm going to make angle D here. We'll call this angle D. So we can say what number this is, right? We can take a protractor and measure it out, and it can be something like 50 degrees. I'm just going to guess here. But what about this? So this angle has two numbers, right? The number inside and the number outside. So the whole circle is 260 degrees. So if this angle inside, internal angle is 50 degrees, excuse my cat in the background. If this internal angle is 50 degrees, then the external angle has to be 360 degrees minus 50, because they both have to add up to 360. So this is going to end up actually being 310 degrees. So then the question is posed, what's the measurement of angle D? Is angle D equal to 310 degrees, or is it equal to 50 degrees? And the answer to that question is, it depends. Um, the most common way of deciding is depending on which you. For the most part, we will go with the smaller number. You will hardly see a situation where 310 degrees is used, as opposed to 50 degrees in this case for angle D. Um, but if someone wants you to use 210 degrees, they can be more specific about it and say they want the exterior angle or they want the positive angle is another way of calling it. So the angle inside here, the 50 degrees, can sometimes be called the negative angle. And the angle outside can sometimes be called the positive angle. I wouldn't worry too much about this specifically. Just keep in mind that it exists and it's a possibility. And when you're given an angle, just keep in mind that there are two sides to it with different numbers. But for the most part, always go with the 50 unless you don't go with the 50. So sometimes always maybe go with the smaller angle. I don't want to get too confusing about it, and I don't want to get too philosophical about this because this is just the basics that we'll need to move on to the more important stuff. So just to recap, angles 360 degrees total, and it's just an arbitrary number we decide to describe the shape, so that we can use it more. Um, sorry, so we can use it more efficiently in future problems and stuff. I'm afraid he's gonna fall off, but you know what? That's just his life. It's prerogative. All right. The other thing we should talk about is the types of angles. So we talked a little bit about obtuse and acute angles, but and also right angles. But let's just list them out just to be safe. So if we have an angle that is exactly 90 degrees, we usually notate that with a little square on the corner. And that's how we let people know that this is supposed to be 90 degrees. If we have, and we call this a right angle. Now, if we have an angle that is smaller than 90 degrees, we've been over this before, but we usually call this an acute angle. I'm going to kick that cat's butt. Okay, so for a bigger angle than 90 degrees, we're going to call that an obtuse angle. And then for, let me just close this up. That's a little better. So there's a couple of different types of angles here. If you have just a straight line here, so a line and then with an angle of 180 degrees, we just call that a straight angle or a straight line. If we have two angles together and they add up to 90 degrees, so let's say we have this angle here, we'll call it A, and then we have this angle here, we'll call B, and it's A plus B is equal to 90 degrees, then we call these two angles complementary angles. And then if we have two angles that add up to 180 degrees or a straight line, then we will call those supplementary angles. So we'll call this A, we'll call this B, and then we'll say that A plus B is equal to 180. We'll have an if statement, and then a then. Supplementary angles. I might have to pause for a bit because that cat is starting to worry me a little bit. Give me 1 second. Let's see, where's the pause button? I'll pause it in editing or something. Give me 1 second. Cat! Get out of here. Okay, sorry, I'm back. Just back to business. All right, so those are the angles. Nothing too crazy here. A little bit of memorization. You just have to remember the names, but they're kind of intuitive. Uh, Acute just makes it feel like, in my brain, acute feels small and obtuse feels big. Um, Straight angle is pretty straightforward. And for as far as complementary and supplementary angles, it's very easy to mix them up if you're not careful. Um, to me, just supplementary sounds like a bigger thing than a complementary. I don't know how to explain it. There are different mnemonic devices out there to help you remember the difference between complementary and supplementary. But I guess the way you can think about it is if you're complementing someone, you and someone are working together for a bigger goal. And if you're supplementing someone, then someone's already pretty big, and you're just helping them out a little bit to. So in the complementary, you have two small things, A and B, working together for a bigger thing, and for a supplementary, you have one big thing like B, and then one small thing like A. Not necessarily useful. You might find a better way to memorize these yourselves. Just a little bit of memorization, not too bad. There's nothing mathematically crazy going on yet. But these are the angles that we have to remember. Let's move on to triangles. And there's not a lot to triangles either. There's only a couple, and I'm going to list them out first, and then we can talk about each individually if we need to. So, for triangles, we have, well, a triangle, let's go over what a triangle is first. A triangle is just a three-sided polygon. And the way that we're going to define triangles is based on their lengths of the sides and the measurement of the angles. Some things to keep in mind about notation is that if we have two line segments that are the same size, we'll notate that by drawing little lines like this to indicate that they're the same size. Let me make this a little better. And if we want to indicate that angles are the same, then we will do something like this. And if there's different angles, but there's some that are the same, some that are not, then we can also notate them by putting little lines on the angle bars themselves. This is just to indicate measurements, because you can never trust a drawing unless it's computer generated. No matter what I draw here, no matter how careful I am, it's never going to be perfectly exact. That's just the nature of the beast with triangles, and just shape and geometry in general. But the first triangle we want to go over, I've already drawn parts of it here, is a triangle where all the angles and all the sides are the same. This triangle is called an equilateral triangle. I spelled it wrong. Mistake. Equilateral. And then I'll just draw a little triangle. Equilateral triangle. The next kind of triangle we want to talk about is the isosceles triangle. And the isosceles triangle is a little more wedge-shaped. And in this triangle, two sides and two angles are the same. But the third side and the third angle are very different. And then there's the ugly duckling of all the triangles, the scalene. And in the scalene, no sides and no angles are the same. The way I remember scalene is that scalene sounds like scary, and it's kind of scary to not have all the sides the same. Equilateral is pretty obvious. All the sides are equal. And then it leaves isosceles as the last one, and isosceles is the one with the two. There are also other mnemonic devices you can look into. I know I'm not too good at those, so I'll leave that to you. But there's a couple more triangles. Similar to the angles, if you have a triangle here with an obtuse angle, this is called an obtuse triangle. That's pretty easy. If you have a triangle with an acute angle, you can guess that it's probably called an acute triangle. And if you have a triangle with a right angle, then this will be called a right triangle. Now, you can have triangles be, let's say, acute and isosceles at the same time. In fact, you can see that right now. And you can have triangles be obtuse and scalene, or right and isosceles, or right and scalene. Um, so the triangles at the top here and the triangles at the bottom here are not exclusive to each other. You can have them mix around and stuff. So those are the triangles we have to work with. Those are the special triangles. Out of those, the one that's going to be really important is going to be the right triangle. You're going to see a lot of that because you'll also find out later on that no matter what triangle you have, you can always turn it into a right triangle. So if you know how to work with right triangles, you know how to work with any triangle. And to demonstrate that real quickly, I'm going to just draw a random triangle. Boop, boop, boop. There it is. This is not a right triangle. These sides are not right, but if I am to go down perpendicular to this, from here, because I'm being perpendicular, these angles are right. And so no matter, even if angle A, angle B, and angle C are not right, angle D is going to be right here. And so then instead of one big triangle that is some random configuration of angles and sides, you can treat this as two right triangles. Where the right angle is angle D. And if we look at this one over here, if we flip this over, then this will be angle A, and this will be angle B. And if we look at this one over here, this one is already over here, so this one is angle C, and this one is angle B. And so now you have two triangles that they're right angles. And like I said, we're going to be going over a lot of theorems and a lot of formulas that help us work with right triangles. So if we could turn anything into a right triangle, we can work with anything, which is pretty cool, right? So if we draw just another random triangle down here with a different shape just to prove my point, let's just draw something more acute, something like that. You can still make this a right triangle by doing the same thing. You can just go perpendicularly down this way, and then these two will be right angles. Or if you prefer, this might be a little bit more work to get it, but if you can figure out the perpendicular line here, then these will be two right angle triangles. All I'm saying is you can turn any triangle to a right triangle, so if you know how to work with them, you can work with anything. Yeah, so just a quick recap of some definitions mostly before we get into any heavy math. Angles, types of angles, and types of triangles. We're going to need to know those. So get comfortable with them enough that if I mention something, you don't have to think about what kind of triangle I'm talking about. If I say, oh, let's look at this scalene triangle and this set of complementary angles, or what, you should be able to know just based on what I'm saying without having to look it up. I don't know how well this turned out, so hopefully it's helpful. I imagine it's not going to be very helpful until the later sessions when we get to the actually hard stuff that a lot of people get to struggle with. But we'll see where this goes. You guys have a good future. I'll see you around.